Let us solve a problem or analyze a problem of Airys stress function in two-dimensional Cartesian coordinates. So the problem is like this: examine the stress distribution. Examine the stress distribution. Represented by the Airys stress function given by so number one, there are two stress functions here. Phi is equal to ax square plus by square, where a and b are constants. And the second one is phi is equal to b into y cube, where b is constant. Now, in such types of problems, so stress distribution means in a two-dimensional Cartesian coordinate system, you will be having three stress components. They are sigma x, sigma y, tau x. So you know that in a two-dimensional Cartesian coordinates, sigma x I am going to take like this, it will be acting like this. Sigma y will be like this, and tau xy will be something like this. So it will be acting like this. So here what happens, there is a definite relationship between these stress functions and the given area, these stress components and the given area stress function. So the relationship is like this. I have explained all this in my earlier video lectures. You can go through that. So sigma x is given by dou square phi by dou y square. Sigma y is given by dou square phi by dou x square, where phi is the area stress function, and tau xy is nothing but minus dou square phi by dou x dou. Actually, a function phi is said to be an area stress function in x and y, provided its fourth, the del power 4 phi is 0. So this is the condition for phi to be an area stress function. So here this del power 4 phi is nothing but dou power 4 phi by dou x power 4 plus 2 times dou square phi by dou power 4 phi by dou x square dou y square plus dou power 4 phi by dou y power 4. So this is the operator. So del power 4 is nothing but this. So that is, this can be expanded in this form. So if given a phi function in terms of x and y, it represents an area stress function only if this condition is satisfied. Of course, in this case we can check that this in the first case it satisfies this condition, because fourth derivative of this function will be 0 because the highest power is 2. Fourth derivative naturally becomes 0 here. Now let me take one by one. I will take the first area stress function ax square plus by square. Let me find out this sigma x, sigma y, tau xy using this definition. So sigma x is dou square phi by dou y square. So this is nothing but dou by dou y of dou phi by dou y. I can write like this. So if you differentiate this with respect to y, so you are treating x as constant. Already a and b are constants. When you are differentiating partially with respect to y, we have to treat x as constant. So then the answer will be here. This is dou by dou y of dou phi by dou y is nothing but the derivative of this will be 0. The derivative of this will be 2by. So if you once again integrate this, differentiate this with respect to y, you will get 2b. So what we got here is sigma x is 2b. That 2b once again is a constant, because b is a constant, 2b is constant. It doesn't depend on x and y values. Similarly, sigma y is dou square phi by dou x square. So in this case it is dou by dou x of dou phi by dou x, which is nothing but dou by dou x of 2ax, because the derivative of this term will become 0 and this is nothing but 2a. If you differentiate this with respect to x, you will get 2a. This is another constant. You can see that this is another constant. That means both sigma x and sigma y, they are constant. They don't depend on either x or y. Then the third stress component is dou xy, which is given by minus 1 dou square phi by dou x dou y. So once we have to differentiate with respect to x, next we have to differentiate with respect to y. So let us see what happens here. This can be written as minus dou by dou x of dou phi by dou y, can split like this. That is minus dou by dou x of dou phi by dou y is nothing but 2by. So that means it is what this becomes 0 here, because this is independent of x. This becomes a constant and becomes 0. That means there is no shear stress term. So here the first value, sigma x value is 2b, constant. Sigma y value is also constant, 2a, and dou xy is 0. Now the question is, we have to plot the stress distribution like this. We have to take an element. I will take an element, two-dimensional element. So let me take the axis of reference at the center. X and y coordinates are like this. This is the origin now. So 0, 0 will be here. Now we have to plot the variation of these stress components on this boundary. So now here, this is the element now. Sigma x is represented like this, sigma y is represented like this, dou x is represented like this. Now how to choose this point is, you can see here, since sigma x is independent of x and y, it is constant. So 2b, let me take that 2b, b as positive. So that means then what happens, sigma x becomes positive if you treat a and b as positive, unless otherwise it is given. So that means irrespective of x and y, the value of sigma x is constant. That means here x may be having some value, and you can extend this side. Here also you can have x value. So irrespective of x and y, it is a constant. That means I can show like this. It represents constant value like this. So sigma x is constant. It won't vary. So this is constant value. This value is 2 times b, and this side also. So this is the value of sigma x. So sigma x is represented like this, and here also this side also it is same. So it is uniform on both sides. Whatever may be the value of x and y, sigma x value is equal to 2b. So sigma x is equal to 2b on either side. It is 2b. So that is what we have to show. Sigma y I have to show now. Once again, it is 2a, treating a as positive. So this is also tensile. So what happens here is, positive value if you get, positive value represents tensile stress. So if you want to show tensile stress, you have to show away from the material like this and like this. So negative value if any, it should be taken as a compressive stress, but anyway in this case you don't have compressive stress. Along both x and y direction it is tensile stress only. Now along y direction also it is constant, so I have to show like this. So this value is 2a. So this is sigma y value, it is equal to 2a. And this is on the other side also, it will be 2a only, like this. So this value is also sigma y, which is 2a. And coming to this shear stress, since it is 0, there is no question of plotting shear stress. So this is how we have to plot the stress distribution given the Airys stress function. This is the first problem. Now for the second problem, let us take phi as by cube. We have taken phi is equal to b into y cube, where b is constant. Now once again we have to adopt the same procedure to find out the stress components. Sigma x is given by dou square phi by dou y square, which is nothing but dou by dou y of dou phi by dou y. So dou phi by dou y here is, it is 3by square. Okay, so dou by dou y of 3by square, and which is nothing but, once again if you differentiate this respect to y partially, 3b into 2y, y square differentiation 2y, that is 6by. So you can see that the value of sigma x is 6by, which is positive, that means tension you can take. Sigma y value will be dou square phi by dou x square, that is dou by dou x of dou phi by dou x. Please note that phi is independent of x, so therefore its derivative with respect to x is 0. So this becomes 0. Dou by x of 0 is also 0. So there is no sigma y component here. Now coming to tau xy is minus dou square phi by dou x dou y, that is nothing but minus dou by dou y of dou phi by dou x. Once again here dou phi by dou x is 0, therefore derivative of that also will be 0. So in the second stress function, given stress function, two components, stress components will be 0, sigma y is 0, tau xy is also 0. Now to plot, here you can observe that sigma x is independent of x. It doesn't depend on x. It depends, it increases. It increases with y. Because sigma x is 6b y. 6b is constant. As y increases, sigma x also will increase. Now, to represent this in a stress distribution diagram, like this, once again I will take x-axis, y-axis, or even like this, 0, 0. X is measured like this, y is measured like this. So anyway, you know that sigma y is 0, there is no sigma y stress component here. Tau xy is 0, there is no shear stress component. Only we have to plot this sigma x component. Here you should see that one thing is very important. Here the value of y is 0 here. Okay, the value of y is 0 here. Therefore, at y is equal to 0, if you put sigma x will be 0. That means the value of y is 0 here. Then as y increases from this point to this point, your stress also will increase, and in the downward direction also, as y increases, y is measured from this line. As y increases downwards also, stress increases. Therefore, this is how it increases. As the y is taken downwards, it is negative. Y is taken upwards, positive. Therefore, the stresses will be of opposite in nature. So here it is tensile, whereas here it is compressive. So please note that. So this stress is tensile stress, because y is positive, sigma x will be positive, that is tensile. When y is measured down this, then it is compressive stress. So but it increases. At y is equal to 0, stress is also 0. For example, this is an example for that bending stress diagram. In a simple rectangular beam, if you take in your strength of materials, you have learned it. Suppose if you take a rectangular section of a beam, centroid, this is the neutral axis. At the neutral axis, your y value will be 0. If you plot the bending stress distribution for this, so you will be getting 0 stress here. F is bending stress, 0 here, and maximum here and here. So depending on whether it is simply supported or cantilever. So if it is simply supported, all the fibers above the neutral axis will be subjected to compression, whereas below it is tension. Whereas if it is cantilever beam, above the neutral axis tension, below the neutral axis is compression. That is this case. Tension above this, compression below this. So this can be taken as an example for bending stress. So bending stress, so you can name it as uniaxial linearly increasing stress field. So this is called as uniaxial linearly increasing, because it's a straight line. This is a straight line, variation is a straight line, linearly increasing stress field. So that this phi is equal to what you can say, By cube represents uniaxially linearly increasing stress field, which is the example for pure bending case. Pure bending of a beam, we have studied in strength of materials. The governing equation for pure bending is M by I is equal to F by Y. So this equation, all this you have derived in strength of materials. So in the for this stress function, stress field, only you have sigma x. So you have only sigma x. You don't have sigma y. You don't have rho xy. Whereas in the first case, this represents a biaxial stress field, of course without shear stress. So you can name this as biaxial stress uniform. You can uniform stress field. See, because you have sigma x is a constant, sigma y is also constant. Biaxial uniform stress field, of course, the shear stress is 0. In some cases, depending on the function, you can have shear stress component also. Then you have to plot the shear stress component also. You can refer the problem which I have done in the earlier video for the same Airys stress function. I have taken a different stress function and I have plotted all the 3 stress components in that problem. So this is how, if a stress Airys stress function is given, you can always compute this 3 stress components in Cartesian coordinates and Cartesian coordinates. You can check whether that phi function satisfies the equation that del power 4 phi is equal to 0. If it satisfies this equation, then phi is a stress Airys stress function. Then you can always plot the stress distribution by getting the partial derivatives and by giving suitable values for x and y and plotting. So if it is if the stress component, say for example, this is stress component directly proportional to y, then it is linear variation will be there. If the stress component is proportional to y square, then it is parabolic variation. So like that, we have to plot the stress components, and then we can get the stress distribution diagram for the material.